study the whole parametric family in one picture. So Solomyak's theorem says the following. We have a two-dimensional function which depends on the parameter and the point in the unit interval, and this two-dimensional function is L2. This is what just a reformulation. It's not using any big arguments. So it means we can consider a two-dimensional function, yeah, and it is an ordinary L2 function. And this function I want to consider in the rest of my talk. So I will consider this rectangle. Here we have t from 1/2 up to 1. Here we have x from 0 up to 1. Yeah? And here on these vertical lines we will have the Bernoulli convolution. On each line we will have 1. And then of course we have to represent them by color code. And here we have the overlap region where the two intervals meet each other and where we have two values for the multi-valued map. Yeah. So let us see first this on the level 3. So here's level 3. I consider just the overlap as I did before, but on each vertical, I do this now together for all parameters. On each vertical line we have one Bernoulli convolution, but only the third level approximation. So for instance, this is the big intersection, and these are the smaller intersections, and in the third stage we have these two still smaller intersections, and we have a mapping which is small here, then it goes up, it has two values here, it goes down to 1, 2, 1, 2, and so on. But here we have already values up to 7, where 7 intervals meet on the level 3. And this can be done now for large level. And this is very interesting. I just, is what I started with, I just want to have all measures in one picture, and I make a program for this picture, and then I see very interesting structure. Yeah. So we have in the two-dimensional picture, we have some structure. Yeah. The structure is not so clear here, but we have the smooth cases. Yeah. Here there is some structure, there's also a piezo number here, here there's not so much, but here at the golden mean the structure begins. Yeah? And we have all these blue lines, and then we may zoom in and look at it for this part left of the golden mean, and you see the blue lines become very clear, and you have also a pattern inside. Yeah? So when you look at the parameter dependence, some structure becomes visible. And now I was very excited, but it turned out, this is the algorithms. You are not so much interested in the algorithms. We can discuss later. So we want to study the structures. So the blue curves are so-called curves of unique address, and inside the overlap region we will find some other structure. So this is the picture. Here we have the golden mean where the structure starts, and here we have all these blue lines coming from the overlap region and going to the well, we have the uniform distribution, the Lebesgue measure. And they all go there, and we have large values. So here where some crossings appear, maybe these are piezo numbers. It has to be studied first. But anyway, it's exciting, yeah, when you have a structure and you want to understand. Yeah.
This is a kind of sunshine.
Yeah, something like that.
In the board.
Yeah. Thank you. Thank you. This is a poetical interpretation. Thank you. So then it turns out, I was not aware of that many people have dealt with the points of unique address. It starts with Erdős and co-authors around 90s, and in fact these are the blue curves. So what I found in my picture is already there in the research, and I should not forget to quote all those people. Especially Nikita Sidorov did a lot of work in this respect. He wrote a lot of papers on the unique addresses. Yeah, okay. So what is the new aspects in my work here? So it is the blue curves are rational functions. The blue curves which you see outside the overlap regions, they are given by such function just as a power series. It's a power series. In fact, the power series, as you see, starts from 0 because I divide by t. It's and the curves, you see, it's interesting, they indicate a quantile of the Bernoulli convolutions. Let me just make this clear. For instance, here, oh no, I have to take the other one. The biggest blue curve is further here. We have the biggest blue curve is here. It starts here and it goes to 1/3. And all Bernoulli convolutions have to measure 1/3 below that blue curve and measure 1/3 between this and the mirror image here, 2/3, and 1/3 upwards. And then you have another blue curve which starts here, just a moment, here, and that's 2/5. It goes to 2/5 here. And always, for all Bernoulli measures, we have 2/5, measure 2/5 up to this curve. So we have some, in the very chaotic picture, we have some smooth element. Okay? These curves give some smooth element and they connect all the parameters. It's interesting to see, so sorry. There's another, I don't know whether you are familiar with the bifurcation diagram. It was very popular in the 90s, and now it's not so popular anymore. And one can find that in fact these lines are very much connected to this one. So the intervals, the gaps in between, they can be described by 0, 1 words, and it's exactly the same words. And so you also have, there's a paper by Sidorov and others on the Tchaikovsky order, but you can also say the whole order of words is the same in these two diagrams. And the reason for it is very simple. It's because both of these, as well as the Mandelbrot set, they are based on the doubling map. The doubling map is just g of x equal 2x mod 1. Yeah, this map where we have no overlap except for the point 1/2. And this is the basis for both the bifurcation diagram of quadratic maps and the Mandelbrot set, and also this one. So one can show that the dynamics of the Bernoulli convolutions outside the region, the overlap region, is just conjugate to this map for every parameter t. Perhaps one can say why, for instance, when we have somewhere here we have 2 over 5, yeah, what this curve means, what it is. It is a curve, or for the 1 over 3 case, it's perhaps not, it's still easier. One can prove the following. We have 1 over 3, when you apply g to this 1 over 3, then 1 over 3 goes to 2 over 3, and 2 over 3 goes to 1 over 3. So that's the simplest periodic point. Yeah? And when we have this for periodic points, we have the point t over 1 plus t, and it goes to by g0, beta x, yeah? It goes to 1 over 1 plus t, and this goes back by g1. So it means that this simple relation, which is true for t equal 1/2, we have this situation, it will be true for the whole curve, and the blue curve, which we have seen there, is just the curve y of t equal t over 1 plus t. So it's just a rational function. All periodic points give rational functions there.
This is a rational function on the theory.
It's a rational function for t between 1/2 and 1.
Okay.
I consider it only from 1/2 to the golden mean, because then the rational function comes into this yellow triangle, and then it has not the property anymore. Because when it comes into the yellow triangle, then you have also another branch of you have also g1 will also work here, and g0 will work here, and you get a larger orbit. So it's, yeah. I'm sorry. So there is something on local dimension.